Today, we will be learning two physics concepts that have lots of applications and uses. These concepts pave today's innovations and serve as the basis of more physics-based technology. The first concept is one of the fundamental forces in the universe, the magnetism. We will define, describe, and list types of magnetism and its useful applications today. Also, we will be introducing famous scientists who were discovered and investigated this kind of force in nature. The second is the remarkable discovery of electromagnetic induction that introduces a more efficient and energy-saving inventions. Moreover, we will be acquainting with some scientists who have spent their lives in determining the relationship of magnetism and electricity. Magnetism was first observed in the form of the mineral magnetite or lodestone, which consists of iron oxide, a chemical compound of iron and oxygen. The ancient Greek were the first known to have used this mineral, which they called a magnet because of its ability to attract other pieces of the same material and iron. The Englishman William Gilbert was the first to investigate the phenomenon of magnetism, systematically using scientific methods. He also discovered that the Earth itself is a weak magnet. Danish physicist Hans Christian Ørsted first suggested a link between electricity and magnetism. Experiments involving the effects of magnetic and electric fields on one another were then conducted by the Frenchman André-Marie Ampère and Englishman Michael Faraday. But it was the Scotsman James Clerk Maxwell who provided the theoretical foundation to the physics of electromagnetism in the 19th century by showing that electricity and magnetism represent different aspects of the same fundamental force field. The present-day understanding of magnetism, based on the theory of the motion and interactions of electrons in atoms, called quantum electrodynamics, stems from the work and theoretical models of the two Germans Ernst Ising and Werner Heisenberg. A magnet has two poles, the south and north poles. A magnet may be a bar magnet, a horseshoe magnet, or a disc magnet. There are three properties of a magnet. Like poles repel each other, unlike poles attract each other, and monopole cannot exist. Magnetism arises from two types of motions of electrons in atoms. First, the motion of the electrons in an orbit around the nucleus, similar to the motion of the planets in our solar system around the Sun. Second, the spin of the electrons around its axis, analogous to the rotation of the Earth on its own axis. The orbital and spin motions independently impart a magnetic moment on each electron, causing each of them to behave as a tiny magnet. Thus, magnetism is a force generated in matter by the motion of electrons within its atoms. How can we find the shape of the magnetic field? In this example, the region in space that is penetrated by the imaginary lines of magnetic force describes a magnetic field. The strength of magnetic field is determined by the number of lines of force per unit area of space. Magnetic fields are created on a large scale either by the passage of an electric current through magnetic metals or by magnetized materials called magnets. The elemental metals iron, cobalt, nickel, and their solid solutions or alloys with related metallic elements are typical materials that respond strongly to magnetic field. On the other note, like all magnets, Earth has a magnetic field. Earth's magnetic field is called the magnetosphere. It is a huge region that extends outward into the space. It stretches from the surfaces to several thousand kilometers in the sky. With this, Earth's magnetic field helps to protect Earth and its organisms. It protects us from the harmful particles given off by the sun. Also, Earth's magnetic field is used for navigation. People use compass to detect Earth's magnetic north and south poles. What are the types of magnetism? There are 5 basic types of magnetism have been observed and classified on the basis of the magnetic behavior of materials in response to magnetic fields at different temperatures. These types of magnetism are ferromagnetism, ferrimagnetism, antiferromagnetism, paramagnetism, and diamagnetism. Ferromagnetism and ferrimagnetism occur when the magnetic moment in magnetic material line up spontaneously at a temperature below the so-called Curie temperature. In ferromagnet, magnetic moments of equal magnitude arrange themselves in parallel to each other. On the other hand, ferrimagnet is when the magnetic moments are unequal in magnitude and order in anti-parallel arrangement. Antiferromagnetism is when the magnetic moments are equal in magnitude and offering occurs at a temperature called the Néel temperature in an anti-parallel array to give no net magnetization. Paramagnetism is a weak form of magnetism observed in substances, which display a positive response to an applied magnetic field. For example, in atoms and molecules with an odd number of electrons, since the net magnetic moment cannot be zero. Diamagnetism is the negative response of matter to an applied magnetic field that prevents the penetration of the field into its interior. It occurs in non-magnetic substances like graphite, copper, silver, and gold, and in the superconducting state of certain elemental compounds. A compass is a simple magnetic instrument. Electromagnets are utilized as key components of transformers in power supplies that convert electrical energy from a wall outlet into direct current energy. High-field superconducting magnets, where superconducting coils generate the magnetic field, provide the magnetic field in MRI or magnetic resonance imaging devices that are now used extensively in hospitals and medical centers. Permanent magnet applications are in loudspeakers, earphones, electric meters, and small motors. When the magnet is moved towards the coil, the pointer or needle of the galvanometer, which is basically a very sensitive center zero moving coil ammeter, will deflect away from its center position in one direction only. When the magnet stops moving and is held stationary with regards to the coil, the needle of the galvanometer returns back to zero as there is no physical movement of the magnetic field. Likewise, when the magnet is moved away from the coil in the other direction, the needle of the galvanometer deflects in the opposite direction with regards to the first, indicating a change in polarity. Then, by moving the magnet back and forth towards the coil, the needle of the galvanometer will deflect right or left, positive or negative, relative to the directional motion of the magnet. Similarly, if the magnet is now held stationary and only the coil is moving towards or away from the magnet, the needle of the galvanometer will deflect either direction. Based from the observations, we can say that a relationship exists between an electrical voltage and changing magnetic field, which is according to Michael Faraday's famous law of electromagnetic induction. Electromagnetic induction states that a voltage is induced in a circuit whenever relative motion exists between a conductor and a magnetic field, and that the magnitude of this voltage is proportional to the rate of change of magnetic flux. In simplest term, Michael Faraday discovered a way of producing an electrical current in a circuit by using only the force of magnetic field. This led to a very important law linking electricity with magnetism. One of the important applications of electromagnetic induction is the generation of alternating current or the use of generator. Other uses that includes electric motors in washing machines to trains, electric hobs, electric cooker, transformers, and guitar pickups. Another specific example made by my students in electronics class is the Faraday's flashlight. They made a prototype based from the given schematic diagram. Magnetic field is the space around the magnet throughout which magnetic force exists. Induced current is created by crossing a magnet over a wire loop. It uses the following electronic devices such as diode, capacitor, and LED. The function of a diode is to restrict the direction of the movement of charge carriers. Essentially, it allows electric current to flow in one direction but blocks it in the opposite direction. The rectifier is constructed from diodes and used to convert AC to DC. In this prototype, it used a full-wave rectifier. A capacitor, on the other hand, is an electrical device that stores the power that is generated. It is used in electrical circuits as energy storage device. How does Faraday's flashlight work? When a magnet inside a coil or loop of wire moves back and forth rapidly, it increases the magnetic force and continuously induces EMF or voltage that would alternate between one positive polarity and a negative polarity, producing an alternating current or movement of electrons that powers the LED. Furthermore, in order to induce more voltage into the coil using magnetism, we can apply the following. First, increase the number of turns of wire in the coil. Second, increase the speed of the relative motion between the coil and magnet. And lastly, increase the strength of the magnetic field or magnet size. Thus, electromagnetic induction was an enormously important discovery for the future of both science and technology. The Faraday's flashlight is one of the innovations linking to electricity and magnetism, in which an electrical current is created in a circuit using only the force of magnetic field.